All right. Good evening, everyone, and welcome to another VKC. Today's special guest speaker is Dr. Yana Fedortchouk from Dalhousie University. Yana received her undergraduate degree in geology from Moscow State University in Russia. She got introduced to the field of experimental petrology, working for a year in the laboratory of alkaline rocks at Verdansky Institute of Geochemistry and Analytical Chemistry in Moscow. Yana continued experimental work at the University of Victoria under the supervision of Dante Canil, where she completed her PhD trying to understand how kimberlite crystallization conditions affect the preservation of diamonds. Parallel to working on her PhD, Yana was doing contract work for BHP Billiton, studying exploration diamond samples from the Ekati diamond mine. After completing her PhD, Yana spent 1 year in Whitehorse for the Yukon Geological Survey, trying to explain reports of enigmatic diamond placer deposits in gold. In 2007, Yana moved to Dalhousie University as an assistant and then an associate professor, where she established a high-temperature, high-pressure lab, where she uses experiments to study the interaction of diamonds and other mantle minerals in kimberlite magma. Before we welcome Yana, we're going to have a few words from Barbara.
I do that beforehand. So just for you that don't know, but quite a lot of you here do know, the glossary that I've been speaking about for 14 years is finally published earlier this month. It's available. There's 2 copies here if you want to actually have a look at it. And there are some not order forms, but forms that tell you how to order it at the introductory price, which is still available despite the date on here, which won't be available for very much longer. So if you're interested, please have a look or talk to me.
Thank you, everyone, for coming. Today I'm going to talk about the dissolution features on diamond surface and what we can learn from them, what actually they tell us. And before I start, I would like to acknowledge the help of the people who were helping with this research and without whose support this research would not be possible. So the experimental work that done up to 3 GPa was done with the help of Dalhousie students, Jihai Zheng, Juyanbi, Njelam Porbas, Erin Kelty. Then experiments at mantle pressures at 6 GPa I was doing in Zurich and Bayreuth with the help of Christian Lepsky, Max Schmidt, and Catherine McCammon. The access to natural diamond parcels was with the help of Ingrid Chin from De Beers and John Carlson, initially BHP Billiton and now Dominion Diamonds. And the financial support for these studies was coming from NSERC and also with the help of De Beers. So in my talk, I'm going to basically spend the first part of the talk walking you through different dissolution features that we see on the diamonds, how they form, and what actually we can learn from them about the conditions of kimberlite emplacement. And then in the second part, I'm going to show some of the new research I was doing on the mantle resorption, so how we can use diamonds to learn about the processes, metasomatic processes in the mantle. So the data that I'm going to show, the conclusions that I'm coming to in this study, they come from studies of natural diamonds and from diamond dissolution experiments. So this is the 2 methods I'm doing at the same time, comparing the results of what I see on one or the other one. In terms of the natural diamonds, typically I would examine populations between 100 and 1,000 of diamonds from certain pipe or from different phases within a pipe. And I was looking on diamonds from several Ekati mine pipes, so from Panda, Grizzly, Leslie, Koala, Misery, and Fox. Also diamonds from Snap Lake Dike and 2 bodies from Arapa cluster from AK-15 intrusion and 3 different phases in BK1 pipe in Arapa. So this is in terms of the natural diamond material. In terms of the experiments, what we mostly do that we take diamond and we put it in some material within a platinum capsule, which we weld. And this could be melt, or it could be fluids of different compositions. And after that, we expose diamond, the whole assembly, to the pressure. So we work between 1 and 3 GPa, which is approximately from 30 kilometers to about 100 kilometers. And also I did experiments at 6 GPa, which is approximately 120 kilometers. So this is looking on the mantle. And then also we heat it up to various temperatures. And then we quench the system and see what happened to the diamond. Also, some experiments were done at atmospheric pressure. And in this case, we just use an open crucible where we put the diamond, and we can either just let the diamond sit there interacting with different fluids, or we also add some melt and see what happens with the melt. But here we can control oxygen fugacity and look on the effect of oxygen fugacity. And typically, of course, also heat it up and expose to the temperature. So the typical duration is between half an hour to up to 3 days. That's what we did. The methods that we use then to characterize the result of the experiments and also to examine the natural diamonds is, of course, the optical microscopy. So looking on the surface features produced, the scanning electron microscopy, but also taking some of these features and looking with the atomic force microscope. This is a typical image, actually the 2 types of images you get on atomic force microscope. And what it is, it's basically a 3D metrical model of the surface. And you can do all kind of analysis through the surface. So for example, I can draw a profile and I'll see exactly the shape of my trigon. In this case, I can measure the angles, I can look on the distances, and we can go as small as, this is for example, 5 micron, but we can actually go smaller to just maybe 3-4 micron probably would be the smallest size where we can actually measure it with a certainty. So before we move on, I want to show you that diamonds actually do have a huge diversity of the different features on the surface. So this is just one compilation from Bartoshinsky, basically just to show you that it is actually a very large diversity. And even a population of diamonds from the same kimberlite pipe could show very many different types of these resorption features that must infer that they were developed at the different conditions, and now they ended up in the same kimberlite magma. In terms of the surface features, we do have, of course, growth features on diamonds. This is probably 2 examples of the growth features, so the step phases and this complex dodecahedra here. And we clearly have dissolution features where the surface is the result of dissolution. And of course, in the alluvial history, diamonds also can develop some of the abrasion marks, so the mechanical wear on the diamonds. But in my talk, I'm going to focus just on the dissolution processes. I think they're the most interesting, and most of the diamonds would have dissolution. Only some would still preserve growth features. And that's what actually happens to the diamonds in the kimberlite, but also in the mantle. So it gives us a clue to the processes in both environments. Resorption goes 2 ways. So first of all, we can, if we take an ideal octahedral diamond, then the resorption is going to modify the crystal shape of the diamond. We start typically with the octahedra or cube, and then it develops into the tetrahexahedron form, so to the rounded forms, and this will be accompanied by the volume loss. So this is, I try to put together a sequence from the natural diamonds. Also, at the same time, we may have development of different edge features on the surface, in these cases, the trigons. And this etching of the diamond surface, it could accompany the volume resorption, or you may have some diamonds with a volume resorption and no edge features, or diamonds that are still octahedrons, but covered with edge features. So it's not always one goes with the other one. This is just some examples here. So you have different cavities and square pits and round pits and trigons. And this type of resorption could either develop just on the octahedral face, or on edges and corners, or on both. So again, it could be one or the other or everything. We'll start with the crystal shape. So what affects the crystal shape of the diamonds? There is a little bit of experimental data on that. This is studies of the group from Novosibirsk, Khokhrikov, and Polyanov. And they were looking how the crystal shape changes during dissolution as a function of oxygen fugacity, which of course will affect the type of the species of the volatiles in the fluid. So this is our typical range, and this is the typical tetrahexahedrons. We don't really see those forms too much, but oxygen fugacity clearly does affect the crystal shape. In this study, they showed transformation of diamonds in carbonate melts, which are volatile-free, which is CO2 containing and water containing. Again, we see that the typical resorption features is what in this study they produce in the presence of water. So the composition also affects the type of the crystal shape resorption. In my study, we also started to look on the ratio between the disappearance of this 111 octahedral phase, so basically degree of rounding, and the weight loss, because they actually not necessarily exactly the same. For example, if you take the octahedral diamond and you dissolve it in a water fluid, then you're very quickly going to start rounding your diamond. If it's a CO2 fluid, then the diamond is going to preserve the octahedral shape much longer. It's going to develop different features, but not changing the crystal shape. So for instance, these two examples started like this diamond. Now they're quite different, but both experienced only 7% of weight loss. So if you see, for example, here, I would have about 60% of weight preservation, so 40% of weight loss. In the water, I would have 0.1% of the octahedral. So it basically will be already THH very long time ago, whereas here I still have more than 10% of the area of octahedral phase preserved. So this is the effect of composition of the fluid. We also found that pressure is very helping to round the diamonds quickly. So this is the study of Jihaijing, and this is all water fluid. So here we're looking on very small change in the weight between 0 to 6% of weight loss, and 1 GPa, 2 GPa, and 3 GPa. And you see that this rounding of diamond at 3 GPa happens much quicker. So basically, we would have only 10% preserved after just about 5% of weight loss. So in other words, if we have fluid available to communicate, to dissolve the diamond, and this fluid was exhaled from the melt at greater depth, it's going to round your diamonds much quicker without significant weight loss. So technically, what does it mean if we find diamond like that? It's not necessarily mean that we lost lots of diamond grade. It could, because basically the conversion into THH would require anywhere between less than 10 to more than 40% of the weight loss, depending on the pressure and the composition of the fluid. So for that reason, the octahedra to THH ratio in your diamond parcel is not really a good proxy for the diamond grade loss or diamond grade preservation. It may actually be more indicative of the depth of the fluid exhalution rather than how much of the diamond weight you lost. Now looking on the crystal appearance. So we're moving from shape to the appearance of the diamonds. Many diamonds show these nice glossy features. So the THH is glossy. You see this is a CM image, really nice flat surfaces. I mean, they're curved, but they're very without any features. You can have some fine striation, and you can have hillocks on this type of diamonds. And there are some diamond parcels that would be dominated by this type of THH, or all THH would be more or less like that. And then you would have other kimberlites where your THH mostly will show frosting. So this is close-up of the frosting formed by these sharp features. And you may have kimberlite pipes where the THH will have this very corrosive surface. This is again a close-up of these corrosion features on the diamonds. And typically, you have in your kimberlite, you either have this, or this, or this, or at least in the same phase. Now, from the experiments, we actually produce these type of features with the striations and hillocks in the CO2 fluid. So water CO2 fluid would produce these nice glossy features. Very similar features to that we produced in a carbonate melt if we have no free fluid in the system. This one is still a little bit tricky. I have some guesses, but we still need to check what is happening here. Possibly looks like it's the fluid at high pressure that have lots of silica dissolved. So it's kind of in between fluid and melt. But those two are quite certain. So you can also have a combination where in this case you have really like rough frosting and some area with a less frosting. And the same here, this is another diamond. So looks like that we may have two phases in the same time differently reacting with the diamond. So now we looked on the shape, on the crystal appearance, and we get into the surface dissolution features, the edge features on the diamonds. So we have three main crystallographic directions. The red is octahedra phase, the green is what would have been a cubic phase, which is typically just a corner, and the yellow is this development of THH rounded faces. And they would have different resorption features on them. So octahedra, this is where we would see negative trigons, positive trigons as well, but as you will see, those can happen in other places too. Hexagons, we can also have layering or laminae or terraces on this face, and step faces. THH, this is where we have striation, also circular pits and hillocks. And in the cubic, we have negatively and positively oriented square pits. So these are the examples. This is an example of negative trigon with a positive trigons development in it. So I just picked this image because it shows two on one image for the sake of space, but we will discuss the situation in a second. Hexagons, this is the circular pits on the diamond. This is the square that develops in the corner, and sometimes you see the square pits developing on the walls of hexagons. And these are the hillocks. And now a few examples of laminae or step faces. So they can be very different. They can be more regular, less regular, and finer and more kind of determined as step faces. Now, how do they form and what we can learn from them? I'll start with negative trigons because probably everyone who worked with diamonds saw them. They're very obvious, you see them in all of the natural parcels on the diamonds. But they can be different. So in this case, here I show a simple example. So you have individual trigons of quite regular shape. In this case, they seem to be more pointed bottom, flat bottom. And here, these two examples, this is a much more complex surface with lots of trigons that coalesce with each other. Here we even have deep hexagonal pits with the step walls. And all of these types of trigons, they're common in different kimberlite pipes. You can have in the same parcel, basically all of this. What do we know from experiments? So in experiments, we can, this is now experimental diamonds. At experiments conducted at 1 GPa, you can produce these trigons, so very, very similar trigons. These type of the complex trigons, we only can produce in experiments at 6 GPa, and we'll talk about the conditions in a second. That would be similar to these ones. So I interpret these type of features as the features produced in the kimberlite magma by interaction with the kimberlitic fluid. Whereas these type of the features, we think they inherited from the mantle. So this is mantle resorption that was preserved probably by mantle xenoliths that surrounded the diamonds, and we can now see them when they come to the surface. We can also, using the atomic force microscope, look in more details on the trigons and see what we can learn from that. So the trigons can have a different outline. They can be striped, they can be slightly curved. They can have different bottom, flat bottom, point bottom, and this round or curved bottom. They also have different wall types. We call this one V, Y, so it's two slopes, and U type for the absence of better term. And also, sometimes they combine both negative and positive trigons together. And depending on the relative length of these red sides and black sides, so the black would be negative and the red will be positive orientation, you can have all the different ratios of the two lengths. So from just negative trigon through hexagons to and truncated trigon to the positive trigons. Now, how does it correlate with the conditions of dissolution of the diamonds? What we found that temperature is important. The higher the temperature, you have fewer trigons, but they're going to be larger. Also, the composition of the fluid important. If we measure the mole proportion of CO2 in aqueous fluid, so then 0 will be no CO2 and 1 will be CO2 with no water. And 0.5 if you have the same molar proportions of water and CO2. This is going to actually very significantly affect the shape of your trigons. So first of all, if you have up to 50% of CO2, from 0 to 50% of CO2 in your fluid, the trigons seem to form this clustering around certain diameter sizes, and the diameters show no correlation with the depth. So the same diameter of the trigon on the same diamond can be just a few nanometers to a couple of microns. And then we see it at 0.5 as well. When we go above 50 mole% of CO2, things start to change slightly. So this is this clustering in the aqueous fluid. As we have more CO2, we start to see some spread of the diameters, so different diameters. And also we see the relationship as they become wider, they become deeper. So this is the transitional compositions. This is just a pure CO2. This is all experiments. Now, if we look on the natural diamonds, and as you see here, my data set for natural diamonds is limited, because apparently it's not that actually that common to find diamond with a nice trigons that are definitely kimberlitic resorption, as one would think they should be. So this is just 3 diamonds from grizzly pipe, 1 diamond from koala, 2 from fox, but actually 6 from misery. And what we see that, for example, in grizzly and koala, again, we see this clustering with no relationship between diameter and the depth, whereas in fox, and especially in misery, we see the range of diameters, the different color here, point bottom and flat bottom trigons. And also we see this relationship as they become wider, they also become deeper, which suggests more of the CO2-rich fluid here. Also, the shape of the trigons as well changing with the proportion of CO2. This is, again, less than 50 molar% of CO2. This is more than 90% of CO2. And the bottom shape is changing of the trigons. In aqueous fluid, we have a larger flat bottom and only very tiny point bottom. And actually, if we do consecutive runs, we see that trigons start from being point bottom and then they grow into flat bottom. As we add CO2 to the system, we start to see these rounded bottom trigons, and also the point bottom trigons start to become larger, so everything shifts to the point bottom trigons. Also, the truncation and the hexagon form changes. So aqueous fluid, we have no truncation, no hexagons. As we have more than 50% of CO2, we start to develop this truncation in our negative trigons. And then in pure CO2, we form trigons and hexagons, both of them. And also the outline is changing. So here you see that it's actually becomes slightly curved also at these transitional compositions. Now, positive trigons. Positive trigons are a bit tricky. They're actually not that common. They have been described in diamonds, but not very often. In all of these samples that I showed you in the beginning from Arapa, Ekati, and Snap-Lake, I only see positive trigons on Snap-Lake diamonds. But on Snap-Lake, I see them everywhere. It just sometimes they're very tiny and you need ACM to start seeing them. They also occur differently than negative trigons. They not only occur on the octahedral face, but they actually cover the whole diamond, including the rounded PHH faces. And also very often we see that they overprint negative trigons. So this is a negative trigon with a tiny positive trigons developing. And this, we think, this is initially negative trigon that was actually converted into the hexagon by growing of these additional positive walls. In experiments, experimental data is again limited on those ones, but mostly they are observed at atmospheric pressure. In fact, at atmospheric pressure, you typically just produce positive trigons, except for some rare situations for the different conditions. And they start to develop at temperatures above 800 degrees and in a range of oxygen fugacities. They have been reported at higher pressure, but only in few experiments that also at very extreme conditions. In terms of the processes, what control the reversal from negative to positive trigons, this is also not very well known. There is an idea from the old paper by the Japanese group that it's the low temperature and high FO2. This is where you produce this reversal. At the same time, they're kind of looking on diamond crystallite. It's theoretically by Angus and Dublé in 1975, suggests that to produce positive trigons, you need the same rate of removal of 2 bonded and 3 bonded carbon atoms, which suggests that this happens when diamond crystallites become very unstable, which again would be happening at atmospheric pressure. So with all of that, again, considering that it's a limited information, we think that probably this is a late near-surface resorption event that doesn't happen in most of the kimberlites, but happen in some. Whether it's a feature of the hypabyssal kimberlite, I don't know. We need more studies on that. But it's actually very interesting to understand when the reversal happens and when the positive trigons develop, because this can give us information about the behavior of the fluid in this system. So you need fluid to produce these features, and you need this fluid at certain depth to produce these features, and also at the temperatures when diamond dissolution is still possible, or diamond resorption. So it has to be still high temperature environment. Now, circular pits. Circular pits also not very common, but we do see them on natural diamonds. And kind of the idea that was around for I think from Robinson work, that it's some bubbles of CO2 that attach to the surface of the diamond, and that's what produces these circular pits. In nature, there is no systematic studies where they occur. Jihai Jiang, in his PhD thesis, looked a little bit just in few diamonds. And for instance, he saw that many of Fox diamonds, about 40%, would show the circular pits, only few percent in Koala and Leslie, and he didn't see any in Grizzly and Panda. But again, this is a very limited data set. I would not yet rely on that. But in terms of the experiments, he found a little bit more. This is the experimentally produced circular pits. And what he found that, first of all, he only see them in the water. As soon as you add CO2, you don't see them. The pressure only at 1 GPa, at least not more than 1 GPa. When the pressure is higher, again, they disappear. And you need a low silica content in your fluid. If you add more silica, then again, they start to disappear. which could explain why we don't see them at high pressure, because at high pressure we can dissolve much more SiO2 in the fluid. And so again, we don't see them. So basically it must be some near surface conditions, low SiO2 content, low CO2, but the temperature is still high for the resorption to occur. In terms of the application, the presence or absence of circular pits may indicate the composition of the fluid at shallow depth. And again, this is one of the ways to look on the fluid, what happens with the fluid as the kimberlite is approaching the surface. Now, the striation laminae in step phases, again, large variety of those. Striation we see produced in experiments at 1 GPa with a fluid. You always produce them, and it's very similar. So again, we think that this type of the striation is a feature of kimberlitic resorption. All of these other features here, we don't see them in experiments at 1, 2, and 3 GPa. But at high pressure, at 6 GPa, in the carbonate silicate melts, so in carbonate melts, we produce very similar type of the features, so all of these terraces. And by the way, at low pressure, the melt is not going to produce any nice resorption. It's going to produce surface graphitization and corrosion. It's only at high pressure the diamonds produce resorption features in the melts. So again, we think that this is a kimberlitic resorption, and all of that is the mantle resorption based on the comparison to the experiments. And now, kind of finishing with the kimberlitic part of the story, I put all of that on this speculative diagram, trying to see, like from the diamonds, we see that the composition of the fluid would vary in terms of water and CO2 proportion. And the depth of fluid exsolution could be variable too. And here I'm trying to speculate what would happen if the fluid is going to get exsolved at a different depth. I don't put any exactly depth constraints here, so it's more on the, not a quantitative, more on the qualitative basis. But basically, let's consider the first case where the water fluid is going, the COH fluid exsolved at relatively high pressure. In this case, this fluid will also carry a significant amount of SiO2, MgO, so it's going to be relatively high density fluid because at high pressure, you can dissolve much more in the fluid. And so this fluid is going to, as we go up, so the bubbles are growing, we create the overpressure, we drive the ascent of the kimberlite. But if it happens fast and the fluid was mixed with the melt initially, it may not actually separate from the melt and will arrive to the surface, opening the pipe and producing the pyroclastic kimberlite. And this kimberlite would have very well-rounded diamonds because the fluid was exsolved at greater depth, but the diamond grade can still be high. Looking on Ekati, I was thinking that misery could be this type of the scenario, because actually in misery we see also more CO2-rich fluid, which could be happening at greater depth. Then the second scenario, we exsolving fluid at intermediate stage. And the fluid here, its density is already in much more contrast with the melt because we're not able to dissolve that much of the silicate there. And this fluid may be able to actually separate from the melt, forming this foam on the top that would first break through and clear the pipe. And then the melt that lost the fluid will fill the pipe with a more coherent type of the kimberlite. And in this case, so this would be an example of probably Grizzly and Leslie, in which case the diamonds are Grizzly and Leslie. And the last scenario where the fluid is exsolved very close to the surface. It also has a large density contrast, of course, with the melt, but it may not have enough time to produce this foam and again form the explosive eruption with a pyroclastic kimberlite, but the diamonds are going to better preserve the octahedral phase, although the grades could actually be lower than in this case. So again, at this point, this is just more attempt to look what could be happening if that's what happens with the fluid and how this is going to affect the diamonds. And then, of course, we can use the morphology of the trigones to see, to look on the composition of the fluid. Now, moving to the mantle metasematism. So this is a diagram you all probably saw, the lithospheric keel here, the graphite diamond stability field, the deep lithospheric roots where at high pressure the temperature is still low, so we have diamonds. And then the kimberlites coming through, bringing the diamonds to the surface. And we know from many different evidence that there is a complex metasomatic processes happening in this lithospheric keel. So we have diamonds growing here, probably due to metasematism. We also have diamonds partially dissolved. And some of these metasomatic events can actually be a trigger for the kimberlitic magmatism as well. So this is an example of the garnet from the xenoliths from a Griffin study in 1999 that shows complex rims with a Harzburgitic diamond in the core, then Lertzalitic garnet on the rim, and then again a Harzburgitic garnet, so variation in chrome and calcium, to see that all of these metasomatic events were changing the composition, and probably you have more than one event that they actually show as a melt metasematism and different melt and fluid metasematism in terms of the distribution of trace elements in the garnet. This is diagrams from Stachel and all, where they show how the composition of rare earth elements in garnet is changing as a response to metasematism with the fluid and with the melt. So all of these garnet studies basically suggest that you have multiple events and you have different metasomatic media producing these changes in the lithospheric mantle. So the mantle-derived diamond resorption could actually provide the record of the number of these events and also the metasomatic agents in the subcratonic mantle. Because unlike garnet, where we have overprint of different signals, the diamond would typically preserve only the latest event, metasomatic event, that this particular diamond was exposed to in the mantle. So for this study, we did experiments at 6 GPa. And here I looked on a simple range of compositions. So pure water, pure CO2, mixed water CO2 fluid, and all of the same, but with added silica, because that's what probably we have in the mantle. And so this is in terms of the fluid, and then also the very similar compositions, but above the solidus where we already have the melt. So this is how the run products look, just to show that we did have fluid. So here are the pocket with the fluid in this silica water system. This is all the debris of from the just water experiment. And again, this is a hole from the diamond that I removed from the capsule. The white is a platinum capsule, and all the debris here with a very out of equilibrium phases, with the graphite, with the coesite, with amorphous silica, with grains of silica. So this is all the fluid where we looked on the water CO2 compositions and everything with SiO2, with silica. In terms of the melt, so we see again from the textures, this is experiment in carbonate silicate melt with a quenched dolomite, diopside, and coesite. And this is again a hole from the diamond, and this is just a quenched dolomite all the way through, so the carbonate melt. Now let's see what happened to the diamonds. So in the fluid, in the water fluid, we produce these nice rounded diamonds, and they're very similar to the water CO2 fluid. So what is typical for them that we have glossy, smooth glossy surfaces. We have this typical detrigonal shape that we see at low pressure. We see simple trigones, flat bottom trigones, and elongated hillocks. So all of that is very similar to many of the diamonds that we see, and also to what we produce at low pressure in experiments. But when we add silica, this is where we produce this frosting, which is similar to the frosting of natural diamonds, I'm still careful about this interpretation because we need to examine better whether it's exactly the same type of frosting or different. But this is where we actually see it. So also we need to remember that the solubility of silicates in aqueous fluid is going to enormously increase with pressure. At 3 GPa, we can dissolve 38% of silicate in aqueous fluid. But at 8 GPa, it's already 78%. So we need to remember that whatever fluid we have in the mantle, it must have lots of silicate dissolved in it. So for that reason, I think that this is not a scenario at all for the mantle resorption. And all of these type of features only the kimberlitic resorption. So my conclusion that basically comparing to the diamonds, we see no evidence of fluid metasematism to be diamond destructive. Now let's look on the melt metasematism. So here silicate carbonate melt and carbonate melt. In the silicate carbonate melt, again, these are different temperatures here. We produce all these different types of the terraces, laminae, the complex negative trigons, basically producing almost the whole range of these features that we see on natural diamonds. In carbonate melt at high temperature, only at high temperature, we produce these very deep pits, some of them hexagonal, that we also see in the natural diamonds. So basically, numerous trigons, laminae and terraces and step faces, complex deep pits with the hexagons, all of that we can produce by varying the proportion of silicate and carbonate in the melt and in a relatively limited range of temperatures. These pictures here shows the examples now from natural. This is all natural resorption. This is all diamonds from Arapa, the two bodies from Arapa. And we see basically these complex features with the deep pits. We see different terraces. So we see this laminae. And almost everything that I showed on the previous slide, we can find, for these features, we can find a match almost for all of these features from the experiments. Now, if we look on the proportion of these different morphologies, then here I combine together the 4 parcels from Arapa, so it's 200 diamonds in total. And this is the distribution of different these mantle resorption morphological groups. And the main one, the more common ones, are these ones with this deep, sometimes hexagonal step-walled trigons and pits. So they seem to make almost 50% of all the diamonds with the mantle resorption. And that's what in experiments we produce in the carbonate melt at high temperature, 1500. So in this diagram, I put together the results of dissolution experiments matching with examples from the natural resorption. So we think that this is the kimberlitic part of the story, and this is the mantle part of the story, which we can now distinguish. And what it tells us that, first of all, the fluids do not produce diamond resorption in the mantle, and the variety of the mantle resorption can be produced by silicate, carbonate, or carbonatitic melts by varying the proportion of silica and slightly varying the temperature. And also we see that this complex type of the resorption makes about 50% of the diamonds with a mantle-derived resorption. So this may suggest of some proto-kimberlitic melt effect here, which would be carbonatitic, and also this is a high temperature. And now what I'm trying to do here is to compare the conditions of metasomatic media with the growth conditions of the diamonds. So this is the diagram from Stachel and Luth, where this is graphite diamond field. Of course, the temperature, the pressure is increasing. The green area is PT estimates from inclusions in diamonds for the formation of diamonds in the lersallitic lithology, and the purple is from the Harzburgites. Also, here we see this pink, the 2 pink lines, is the solidus for lertsolite with water and CO2. So it means that above these lines, if we have fluid, COH fluid in the system, in the lertsolite is going to melt and produce partial melts. This line is for the Harsburgite. So in this area here, where the lertsolite, where we have many of the diamonds form, where lertsolite is already will start melting in the presence of fluid, Harsburgite is still going to be solid. So you're going to have the rock and the fluid. So basically here where you're going to have fluid in the Harsburgite. And the kind of another speculation that I put here, that if you have influx of the fluid in the Harsburgitic lithology, then you start to produce, of course, metasematism by this fluid, you enrich in your rock, and you also precipitate in the diamonds. We know that many diamonds are associated with Harsburgites. But as you do that, you enrich your Harsburgite and you can transform it into the lertsolite. And that's what was shown, for example, in these garnets from the Griffin study. So as you do that, you start to produce partial melt, because at the same conditions, in the presence of fluid, lertsolite is going to melt. And this melt is now going to start resorbing your diamonds that you just grow. And then if you remove the melt, then of course the process stops here, and depletion of the lertsolite into the Harsburgite could start the new cycle again. So this may explain some of these patterns of growth and resorption on the diamonds without actually changing even PT conditions. So through this cycle of fluid influx, partial melting, and then depletion, and then the cycle starting again. Basically multiple metasomatic events modifying the composition and also growing or resorbing the diamonds. So some of the further questions that I think would be interesting to look using the diamond resorption. First of all, the formation and evolution of composition of kimberlitic fluid during the ascent, and how it also affects the texture of different kimberlites, depending on the emplacement mode. This, looking on the diamond resorption and specifically on the features that characteristic of the depth of exsolution, the CO2 concentration in the fluid, it could actually provide a nice record and maybe more robust record than anything. And probably not just the diamonds, but other metal minerals too. Also using the diamond dissolution features to monitor the presence and composition of fluid in different magma batches in the last 30 kilometers of ascent. And this would require better understanding of the reversal of these positive and negative trigons. And in terms of the mental derived resorption, I think that if these studies are combined with the isotopic and inclusion studies, it could really help to better understand the sequence and the nature of mental metasematism. And actually, we still don't have a good ore forming model for diamonds in the mantle, which because we don't really understand very well the whole process, what control the growth of the diamonds. So thank you for your attention, and I'm happy to take the questions. Yeah.
Hey, when you talk about ore forming processes, do you mean looking at resorption as sort of the opposite of growth, looking at the features of resorption, what caused them, and trying to say the same types of features in reverse would be related to growth?
Well, technically speaking, it is a reversal process, and we see that the same things like, for example, water producing similar effect during the resorption and the growth. But of course, for understanding diamond growth, it's better to do diamond growth experiments than diamond resorption trying to go back. I was more thinking from that we eliminate the mental metasomatic process that are not resorbing, and so therefore the fluids, they're not resorbing, but they were proposed to actually be the diamond growth media, which agrees with what we see from the experiments, because we see no evidence that the fluids would resorb diamonds. We see evidence that melts resorb diamonds, but no evidence that fluid will resorb diamond. Mm-hmm.
But when you mentioned step phases as one of features of dissolution, so you ascribed only to dissolution resorption,
Mm-hmm.
but I've seen in the literature also some cues that would explain the stepped features as the growth features.
Yes, they can be both.
Can you
So,
distinguish based on what we see maybe in geometry of the stepping?
I don't have a quantitative data. What we did, we would cut a corner of the diamond with the step faces, and we will look with on the pattern, with the CL on the pattern, to see whether it's actually cutting the growth pattern or whether it's corresponding to the growth pattern. And we would see that some are clearly the resorption. And also in experiments, we know that if we start from diamond with no step faces and we end up with the step faces, and we're losing the weight, then this is the result of resorption. So far, when I look on the natural diamonds, I just go by appearance. Sometimes it's obvious that it's nice growth feature. Sometimes I see that it's these irregular features that clearly is similar to the resorption. And I may have situations in between where I would just mark that I cannot determine what it is. But I think it could be done quantitatively. I haven't done it. Mm-hmm.
You see these features on distribution of the size of the diamonds? Or are there different features in very small diamonds? Larger diamonds?
No, typically it's the same, and the smaller diamonds often fragments of the larger diamonds. The difference that, for instance, you may have more of the cubes in smaller sizes and less cubes in the larger sizes. But if you look on the same type, if we just select the octahedra and THH, then it's all the same features. I didn't see any correlation with the size. Although I should say that I didn't try to, and maybe I never had a big enough sample to statistically demonstrate that there is no difference with the sizes.
What sizes?
It varies. Typically, like I looked on diamonds up to a few millimeters, but usually around 1-2 millimeters, and then down. And the down, it really depends if I can tell anything about the diamond. So if I have even a third of the diamond and I already identified what are the resorption features in this kimberlite, I could still use it because I see what it is. But if it's something that I just see an age and I don't really know how I should describe it, then I just put it aside. So it's more the breakage than the size itself.
One of the first slides you showed about the weight loss and how it reacts to the presence of water or carbon dioxide in the fluid, and you said both would, you can have 7-8% weight loss, but completely different morphology. So then if you're not rounding the diamonds with that weight loss, does it mean that you uniformly just reducing the diamond and it still be octahedral but with a smaller weight?
In CO2, you would still end up with a rounded diamond, but you will have to get way more weight loss to get to this rounded shape than if you have a water fluid. Also, it's a THH, it's always curved, and the curvature is different. So in the water, you basically curve it without much of changing. Whereas in CO2, you really remove the diamond to get to this rounded shape. But when people just look, typically when people describe THH, nobody measure the curvature. I think the curvature would be another indicator, but nobody really measure the curvature. But for instance, if you find the kimberlite, the parcel, diamond parcel, and it's mostly THH, very few octas, it's not necessarily that it lost lots of weight, or maybe it lost even less weight than some of your parcels where you have way more octahedral diamonds. And actually, why I was thinking that, because Misery has 4 times grade of all the other pipes around, and it has the largest proportion of these rounded diamonds.
When you like go from octahedral to dodecahedral, those dragons, they tend to decrease, right, as the resorption class. Because like in impressional collection, only the octahedrals have these features. Then the dodecahedrals, the rounded ones, they don't have many characteristics on the surface.
Yes, so for the negative trigones, you still need a remnant of octahedral phase. Once octahedral phase is gone, you have no negative trigones. And often what you see that you have a remnant of your octahedral phase, and the trigone that was there, it's actually partially eaten by the development of the THH phase. At the same time, we need to remember that trigones also, it's kind of a very active process of nucleation and disappearance of the trigones, because you're still removing carbon atoms from the surface. And if you do a sequence of experiments, you see how you nucleate a small trigone, how this trigone in the next experiment it's grow, and then in the next experiment it's gone. And you have trigone in a different place where you have the defects. Yeah, Evan.
Do you think there might be anything to learn from looking at sublithospheric diamonds, super deep diamonds? We know that they generally have a lot more resorption.
Yeah, I'm sure.
Been through this unusual journey that we really don't know anything about.
Yeah, I'm sure if you have diamonds, we can definitely look on them. And experiments can be done now at almost any pressure. Actually, diamond anvil, you have diamond right there. You don't even need to put anything. Yes, for sure. We can talk about that.